Everyone, my name is Will from Sierra and the Department of Physics and Astronomy at Northwestern University. Advised by Professor Shane Larson, our topic for the 13th International LISA Symposium is simulating the extragalactic binary confusion foreground. So let's start. We begin by an introduction for this talk. Our presentation is formatted as follows. We will briefly introduce LISA and gravitational wave signals, following by binary confusion foreground simulation. That is where we will talk about binary system, where we find the potential sources and how do we simulate their gravitational wave signals, and summary with future extensions. So first, LISA and gravitational wave signals. I am sure many of you will be familiar with this picture. The LISA detection frequency band is the richest part of gravitational wave spectrum. Among the predicted detectable objects, which I will not speak about individually in details, one of the most significant and the most numerous type of sources is the compact binaries in the galaxies. And that is the focus of this project. To detect those signals comes LISA. Here shows the LISA sensitivity curve throughout 0.1 to 100 megahertz detection frequency band. There are things we can detect, that is the area above the LISA curve, and things we cannot. However, as shown in the bottom left of the LISA curve, there is a gray area called confusion foreground. That is the signals from those sources will be detected by LISA, but due to their astrophysical properties, they confuse us. So our job is to understand this confusion foreground, improved analysis of the gravitational wave signal detection, and potentially increase LISA's sensitivity. Before getting into the details of the confusion foreground, we take a step back and start at gravitational wave sources. Of course, LISA frequency band covers the richest part of the gravitational wave spectrum. In particular, we will be focusing on a certain type of the source, the binary system. It is rare for a stellar mass object in the universe to be companionless. Theory suggests that about half of the binaries form sufficiently small orbits to interact and evolve into compact system, the shortest period of which is known as the ultra-compact binaries, often with white dwarfs, neutron stars, and stellar mass black holes. And there are important sources of gravitational wave in the millihertz frequency band. During the 4-year mission of LISA, it is expected to detect 10 to the power 3 to the 10 to the power 4 resolved or so-called individual objects. That is the signal to noise ratio bigger than 7 and shown in the picture as light blue. The rest of them, however, those with familiar frequencies to the other sources, overlapping signals, that is if two sources speaking in the same tone, so we cannot distinguish between them, or with low amplitude, has a predicted number of around 10 to the power 7, becoming the astrophysical noise. In contrary to the resolved case, we call that the confusion foreground, and that is the region we previously mentioned, the gray area and the bottom left of the LISA curve. So where are those ultra-compact binaries? We know that they not only exist in the Milky Way, but also in the other galaxies. So to locate our potential source, let's take a look at what is beyond the Milky Way. We start at the origin, the Milky Way, which is a pretty typical barred spiral galaxy, has 100 to 400 billion stars with a diameter of around 60 kiloparsec. If we keep going, reaching the nearest galaxy M31, also known as the Andromeda Galaxy, that is around 770 kiloparsec away. We go further and arrive at the edge of the local group that has more than 54 galaxies, including Milky Way and M31, which has a diameter of around 3 megaparsec. Further away is the Virgo cluster, which has more than 100 galaxy groups and an expand of around 33 megaparsec. We keep going and you think I will show you a pretty picture of the whole universe, but no. Eventually, we get close to the edge of the observable universe, which is an arbitrary definition because it often depends on the electromagnetic observation instrument, which differs and always evolving. So we set our goal to the search area to be the nearby mapped universe of around 100 megaparsec. Now we have an idea of what we are looking for. The next step is to simulate the signals. Obviously, we don't want to put the potential sources anywhere in the universe, so to get a realistic location of the source, we use a current available electromagnetic observation to guide our simulation. Here we introduce GWGC, the Gravitational Wave Galaxy Catalogue, constructed by 4 independent previous catalogs, which has an observation depth of around 100 megaparsec, including about 53,000 galaxies and 150 globular clusters. Each galaxy serves as a location for many of the potential compact binary systems. And here is what the 53,000 galaxies of GWGC catalog looks like. Now we have the catalog. We need to be able to identify the group of each source. So to do that, we can categorize them in a distance distribution, which has 2 advantages. First, the strongest signals will usually come from a close galaxy, other than the Milky Way, of course, or an area with high star density. Secondly, in a more practical way, it is more reasonable to simulate objects that are physically closer together. The details of the simulation will be given later, and here we are only showing an example of how to select the galaxies of Virgo clusters from the catalog. With known information of the Virgo cluster, like the parameters of location, radius, and populations, we're able to single them out from the distance distribution. So with that, back to the map, this is a process of identifying groups of galaxies from the optical observations catalog. For instance, we are seeing the globular clusters, Virgo clusters, and having the information of our potential sources ready, we will move on to the simulation. Here we introduce the simulation tool we use to generate the binary population, COSMIC. The Compact Object Synthesis and Monte Carlo Investigation Code, which is a community-developed and publicly available software based on the legacy of BSE, Binary Stellar Evolution Code from 2002. With significant astrophysical improvement, which means the physics is better, compared to traditional binary system, simulation code, COSMIC is also computationally improved, which means COSMIC generates a fixed population, and Monte Carlo draw the whole galaxy from it. So it doesn't have to go through the simulation of every involving process. Long story short, it is smarter and faster. It was designed for generating realistic Milky Way binary populations specifically, but with modifications, it can be the perfect tool for simulating extragalactic binary gravitational wave sources as well. So this is what COSMIC takes and what it gives us for the input parameters. To the left, we provide the galaxy's metallicity, star formation history, and the number of stars as prior information for the simulation. As for the output, COSMIC gives us the stellar evolution states, that is, if the final binary system is a white dwarf system, double neutron star system, stellar mass black holes, or so, it gives the fixed binary population, and with astrophysical parameters, like the locations, we're able to generate a realistic gravitational wave signal catalog. Having this awesome simulation tool, next, we need to find input parameters. Here we only talk about 2 of the most important ones as example, the galaxy mass and metallicity. All of the prior information about the source galaxies are from previously introduced observational data, GWGC, if you still remember, which includes the optical properties like morphological types and luminosity, not the mass. So to estimate the mass of a galaxy, we take its morphological information or the Hubble sequence, which gives us the galaxy type, elliptical, early stage or spiral, older stage of spiral, irregular, etc. In total, 7 classifications in total. Each type corresponds to a certain mass to light ratio due to its history and star forming rate. From there, we can estimate the galaxy mass from its luminosity. For the metallicity, a pretty similar story. Previously, research suggests different methods of estimating metallicity from galaxy properties like mass metallicity relationship and luminosity metallicity relationship. In the end, GWGC provides us enough information of the potential sources of cosmic to generate a realistic population of extragalactic binary confusion foreground. But last but not least, for the simulation is the categorization. We have the map of gravitational wave sources, but we cannot simulate 50,000 galaxies. As a reference, for cosmic to generate a Milky Way-like galaxy population takes around 6 to 8 hours on QUEST, the Northwestern Research Supercomputer. So for the universe, maybe around 40 years. So our simulation is to categorize the sources into groups, and we break the nearby universe catalog into several categories with similar properties, like metallicity. We generate one fixed population for the whole category, then applied astrophysical parameters to the member of this group. In the end, we merge them to form the complete gravitational wave signal catalog back together. So we are expecting, in the end, to have a simulated realistic extragalactic binary population. With that, to better understand the confusion foreground, here is an example for the binary population of Milky Way, done using Cosmic, of course, by Dr. Braverick and the members of Sierra at Northwestern. Each point here represents a resolved case of binary system that can be detected by LISA. The complete map of extragalactic binary confusion foreground thus is expected to be done in the fall. And to summarize, we are trying to simulate an astrophysical binary confusion foreground of the nearby universe to 100 megaparsec, guided by the Optical Galaxy Catalogue, GWGC. And we introduced this amazing simulation software, Cosmic, which can generate a realistic extragalactic binary population. Once we have the simulation result, we will be able to better understand the confusion foreground and hopefully answer questions like, is there any nearby strong gravitational wave signal contributions? Does the binary population from outside Milky Way, like the Virgo cluster, provides gravitational wave signal strong enough to be able to detect it by LISA and distinguished by LISA? At the meantime, we're going to make a publicly available gravitational wave signal catalog for the future related research and maybe convenience of the community. So thank you very much. I will be happy to take any questions, and I would like to take this opportunity to make the best wishes to the LISA mission, which hopefully will be launched around 2030. So thank you again.